Hello, this is Blaine. My partners are Joe and Sajad, and our project name was Wind to Ammonia. This project was actually an adaptation upon last year's project, which was essentially using Aspen to model the Haberbash process, or an adaptation of the Haberbash process, where we take hydrogen and nitrogen streams and combine them to pressurize them and produce ammonia, which can then be used as a fertilizer for industrial uses or agricultural uses. One of the biggest issues that comes with using the Haberbash process for a full-scale industrial production of ammonia for use in fertilizer is that it requires the use of non-renewable energy source, which would be fossil fuels, and this can create a significant amount of carbon dioxide and is responsible for about 1.3% of the global emissions of carbon dioxide. And our goal in using our model is to integrate a different energy source, which would be wind power or electricity derived from wind power, and integrate that into a system that would not produce carbon dioxide emissions and would also increase the overall efficiency of the wind farms from which the electricity was derived. In order to integrate our wind energy source efficiently into our production, it required that that energy source be intermittent and that it be taken in times of excess. So when the wind energy has overflown on the grid, we take that overflow and integrate it into our production so that not only does the wind farm increase its overall efficiency by not wasting that energy, but it also gets funneled into our production, which can be used to produce fertilizer at a significant scale. One of the biggest obstacles or constraints to our design process was that we are competing directly against a full-scale operation that would use natural gas or fossil fuels and would have no limit to its scale, while our system would have to be a smaller scale due to the intermittent nature of the wind energy source. In order to deal with these constraints, we had to run through quite a few options regarding what resources we would use, what kind of reactions we would run, whether to use catalysis or just separation, use absorption versus distillation for our separation processes. But the main one was whether or not we would use a pure hydrogen and nitrogen source and buy that, or we would produce our own source. So our options for producing a hydrogen stream came down to electrolysis, which is the one that we ended up using, which is essentially splitting water apart to produce oxygen and hydrogen streams. Another option would have been combusting methane or reacting methane in order to produce carbon dioxide and hydrogen, as well as a little bit of carbon monoxide, which was the reason why we didn't choose it, because carbon monoxide is a bit toxic. And our options for nitrogen stream were to either purchase that or to capture it from the air, because air is easily accessible and also has a high concentration of nitrogen. We ended up choosing to purchase liquid nitrogen instead of capturing it from the air, just for the overall energy efficiency of our system and cost efficiency as well. But for the hydrogen stream, we chose to use electrolysis, which takes deionized water and essentially splits it apart using a cathode and an anode and a membrane separator in order to produce a pure hydrogen stream and a pure oxygen stream. And that pure hydrogen stream can be used later on for the ammonia synthesis process after it's compressed. The Haberbash process capitalizes on a very simple equilibrium concept, which is that when you have an equilibrium reaction, increasing the pressure will drive that reaction towards the direction in which it has less moles, which basically means that increasing the pressure will make those products or reactants want to take up less space, so they'll be driven towards the ammonia production because there are fewer ammonia molecules than there are hydrogen and nitrogen molecules in the reaction side. With that being said, a high pressure is not always energy efficient, so we had to choose a pressure that was energy efficient but also efficient in terms of driving the equilibrium towards ammonia production. So in order to do that, we chose a pressure of about 200 bar, and we took our hydrogen streams that we had produced from our electrolysis process and pressurized it to 200 bar And we did the same for our nitrogen stream and pressurized that using a compressor to about 200 bar. And then after that, these two streams, the pressurized streams, were mixed together. And keep in mind that the nitrogen stream was liquid, and liquid nitrogen is quite cold. But in order for our reaction to proceed properly, we needed to maintain a higher temperature than what they were at when they were mixed. So just downstream of the mixer, we had a heater in which both of the reactants would enter the mixer and then the heater in order to heat up to about 500 degrees Celsius. So 500 degrees Celsius and 200 bar would produce an optimum range of our reaction that would drive it towards our ammonia production. After the reactants had been heated up, they would enter the reactor at a high pressure and high temperature in order to form ammonia. And after this, we did have some impurities being both of the reactants. So in order to separate the hydrogen and nitrogen, as well as a little bit of water from the ammonia product stream, we ran it through a condenser and a separator so we could recycle that hydrogen and nitrogen back into the mixer, and it could be used later on in the process while also producing a high purity ammonia stream. So overall, we had two reactants, which were our pure water or our deionized water, as well as our nitrogen feed, which we purchased instead of capturing from the atmosphere. And we had two products, which were our pure ammonia stream, and our purity was about 98%, which is slightly under the commercially viable range of purity, but we produced about 870 kilograms per hour of ammonia. And our second product was our oxygen, which we produced at about 1,600 kilograms per hour, and this was vented straight into the atmosphere. So looking at our electrolysis process, we took deionized water and put it into an electrolysis unit, which separated the water into two H+, which two hydrogen ions, as well as an oxygen that would be negatively charged. Then we place it into a membrane separator, which would separate the oxygen, the negatively charged oxygen, from the positively charged hydrogen ions. And the positively charged hydrogen ions would flow into the cathode because the cathode is negative. Negative attracts positive. And the same goes for the anode. The anode is positive, so it attracts the negative oxygen ion. After the oxygen and hydrogen had been separated, two oxygen molecules that were separated in that process would combine to form diatomic oxygen, which would then be vented off into the atmosphere, and this would be non-toxic. The hydrogen stream would take the two positively charged hydrogens and form diatomic hydrogen, which would then be used later on in the process for our ammonia synthesis. The electrolysis was carried out at about 80 degrees Celsius and 15 bar, which is about 14.8 ATM, which allowed us to produce the product streams at about 99% purity. After our Aspen model had been fully optimized and completed, we ran it through a life cycle assessment or life cycle analysis using OpenLCA to break it down into a few key inputs and a few key outputs that would generally describe the overall efficiency and effectiveness of our model. So one key input that was a bit disappointing was our required energy input, which is about 95 megajoules per kilogram of ammonia. And all of these values in the table listed are normalized to 1 kilogram of ammonia produced. And the bottom half of that table lists all the outputs, being the recovered ammonia, which would obviously be 1 because the system is normalized to 1 kilogram of ammonia. And our unrecovered ammonia was only 0.01 kilograms per kilogram of ammonia. Then our hydrogen and nitrogen were quite low, which is good, and our oxygen output was quite high. A few key takeaways from the conclusions drawn from our model was that it does produce a pretty significantly clean or pure ammonia product stream at about 98%, which is unfortunately below the line of commercial viability in terms of ammonia production. We would want something like 99.5% purity in order to be viable for fertilizer production or fertilizer usage. So ideally, we would want to raise that purity up beyond 99.5% in the future. But one of the biggest downfalls of our system was that The amount of energy that it requires to produce 1 kilogram of ammonia per hour tells us that using about 0.25 megawatts, we could only produce about 6.5 kilograms of ammonia every hour, which is not near enough to satisfy the current demand for fertilizer production. So in order to make this process commercially viable, we would definitely need to increase the overall efficiency of the system so that we could produce a more significant amount of ammonia every hour in order to satisfy the current demand for fertilizer. We have a few ideas for future projects that we could tweak and change our process in order to achieve commercial viability. And one of those would be to just improve upon the electrolysis process by reducing its overall energy consumption and increasing energy efficiency so that it would be similar or close to that of a full-scale process. Another one would be to use a different kind of unit in the Aspen modeling process, which is called the radfrac. This could be used to increase the purity of the ammonia product stream. And the last option would be finding a way to reduce the overall energy consumption by utilizing some of the energy that's wasted from heating up the reactants and finding an alternative method of heating the streams in order to reduce the electricity requirement for the system to operate.